Processes. Introduction. A busbar system comprises several sub-assemblies, and each of them undergo manufacturing and assembly processes. 6 of the important, among many, are detailed herein. These are welding, jointing, plating, painting, coating, and galvanizing. The processes are carried out on the surfaces of conductors, enclosures, and support structures. The Table 4.1 lists the main purpose of subjecting different components of the busbar system to the described processes. The processes are carried out on the surfaces of conductors, enclosures, and support structures. Welding. 3 different metals that are subjected to welding in the manufacture of busbar systems. Steel, aluminium, copper. Welding technology is a very specialized field. There are several welding techniques that are very sophisticated and customized for various industries. Only the most commonly used welding processes that are relevant to the manufacture of the busbar systems and adequate for the purposes are described. Specialized processes such as friction welding, explosion welding, electroslag welding, ultrasonic welding, electron beam welding, laser beam welding, and other methods of welding are not discussed. There are guidelines for effecting the welding of steel, aluminium, and copper. These include the type of edge preparation, root gap, preheating temperature, the diameter of filler rods, gas nozzle diameter, type of gas, gas flow, welding electrical parameters, etc. Every industry must develop its welding manual depending upon the nature of the job and ambient conditions. Welding jigs and fixtures are industry and product specific. While some universal fixtures and manipulators are available in the market, most industries develop their fixtures based on their specific needs. Despite all the written inputs, the quality of manual welding depends on the skill and experience of the welder. The certification of welders is a well-defined and regulated activity. Steel welding. Steel is used in the busbar systems for the manufacture of indoor and outdoor support steel structures and enclosures of non-segregated and segregated phase bus. Depending upon the thickness of metal, 2 types of welding processes are generally adopted: manual metal arc, MMA, and metal active gas, MAG, also known as CO2 welding. Steel sections, used to support steel structures, are heavy, with a thickness of 6 mm, quarter inch, or more. Steel sections, used for the manufacture of enclosures of bus duct, are much thinner, with section thicknesses varying from 3 mm, 1/8 inch, to less. Steel structures are often galvanized after fabrication. The quality of the weld is important to ensure good galvanization. It is necessary to design the support structure so that welding and subsequent galvanizing can be carried out most efficiently. In a good design, molten zinc should flow uniformly over the surface and not get trapped in the crevices during the dipping process. A good weld will ensure that there are no surface defects and there is no possibility of chemical entrapment during pickling operation before galvanizing. Aluminium welding. Welding of aluminium sheets and bars is now an established practice in the bus industry. Aluminium laminates are also manufactured by welding the solid tabs to either end of prefabricated laminates. Aluminium welding is extensively adopted for the manufacture of conductors and enclosures for isolated phase bus, segregated and non-segregated phase bus, gas-insulated bus, high-voltage open bus in switchyards, and high-current open bus DC connections in metal extraction plants. Tungsten inert gas, TIG, welding and metal inert gas, MIG, welding are adopted for the welding of aluminium. TIG welding is generally limited to thin sections up to 3 mm, 1/8 inch, while MIG welding is carried out for thicker sections. Because of the low melting point of aluminium, preheating is not required for MIG welding unless the welding is being carried out under low ambient temperature and the sections are large. Copper welding. Copper welding in the manufacture of busbar systems is now limited to welding tabs to meet the requirements of terminations and orientations. A bolted joint is an alternative solution. However, every bolted joint may require plating, fixings, boots, and accessibility to reach the location, all of which will be far more expensive than welding. Copper laminates were fabricated like aluminium laminates. Solid tabs were welded to a stack of laminates. With the development of resistance weld technology, which gives much better results, this method of making laminates has now become obsolete. However, site welding of laminates to terminals in arc furnaces and similar applications is still being carried out. TIG welding and MIG welding are adopted for the welding of copper. TIG welding is generally limited to thin sections, while MIG welding is carried out on thicker sections. Because of the high melting point and very high thermal conductivity, to obtain a satisfactory weld, it may be necessary to preheat the conductor before welding. The preheating temperature will depend upon the thickness of the conductor. It is recommended to preheat the conductor of thickness over 3 mm. For fusion to take place, there must be an adequate weld pool. Preheating will lead to a change in the mechanical properties, especially on cold-worked conductors. Welding of copper is limited to flat and round bars and round tubes. The welding procedures for these are well established and documented. Welding of copper at the site is rare and not recommended. Methods of welding. The welding method adopted in the manufacture of busbar systems is product-specific. The industry has matured and there is near unanimity on the method to be adopted for a specific metal, based on its application and desired performance. Shielded metal arc welding, SMAW, or manual metal arc welding, MMAW. Gas metal arc welding, GMAW. Flux cord arc welding, FCAW. Electric resistance welding, ERU. Types of welded joints. Depending upon the profile of the job, the following types of welded joints are most common. Before the commencement of the welding process, the mating surfaces have to be shaped and thoroughly cleaned. The operations are called edge preparation and weld preparation. While there are general guidelines for such preparations, each manufacturer may follow his practices depending upon the specific requirement of the job and the available infrastructure. Quality of weld. Defects in the weld are caused by several factors including, among others, incorrect settings on the welding machine, poor quality of welding consumables, variations in metal composition, improper edge preparation, unfavorable ambient conditions, and not following procedures and method statements. The skill of the welder is one of the most important factors in achieving good weld. Most of the defects can be identified by visual inspection and non-destructive testing methods. A weld should have a reasonably smooth, uniform, and consistent appearance. Acceptance norms vary for different industries. The nuclear industry and pressure vessel manufacturers have stringent acceptance norms for different reasons. Welds in the bus industry need not be subjected to such standards. It needs to establish acceptance criteria that are fit for purpose. Defects in welding can be classified into external and internal defects. The external defects are surface crack, overlap, undercut, underfill, excess penetration, spatter, surface porosity, distortion, profile, crater formation, excess convexity, oxidation. The internal defects are slag inclusion, subsurface cracks, internal porosity, incomplete fusion, incomplete penetration. Non-destructive testing. All welds carried out at works in the site need to be inspected to establish that they are fit for purpose. The inspection regime will depend upon the application to which the component is put to use. The welds are subject to inspection as per the inspection plan that is either specified in the standards or agreed to between various stakeholders. Depending upon the type of busbar system, welding may be required to be carried out both at works and at the site where it is installed. The quality assurance plan for manufacture at works and installation at the site are different. The entire welding inspection plan may comprise a combination of different testing procedures. Visual examination. A visual examination by a trained inspector is the most cost-effective way of carrying out this activity. But it can only recognize the surface defects that are visible and draw subsequent inferences. For internal quality and defects, other types of tests are required for certification. Surface crack detection, dye penetrant test, DPT, and magnetic particle test, MPT, are the most common testing procedures followed for the detection of surface cracks. Dye penetrant test. Dye penetrant test is also referred to as liquid penetrant test, LPT. This test can only detect the surface breaking discontinuities or hairline cracks on the surface. Any discontinuity that is embedded inside the weld cannot be detected by this method. It is also not suitable for porous or rough surfaces where the interpretation of the test result could be misleading. It cannot detect a lack of fusion in a weld. It is one of the most prevalent methods of testing in the bus industry and can be used for weld inspection of ferrous as well as non-ferrous material. Magnetic particle test. Magnetic particle test, MPT, can be performed only on ferromagnetic material. The test object is subjected to a uniform magnetic field. On a homogeneous test piece, the flux lines will have a streamlined flow. Any non-magnetic object or a void that is embedded in its path will distort the flux lines. A magnetic probe, scanning the surface, can detect these discontinuities. These can be observed by the field patterns or accumulations of the magnetic particles. Some of the test pieces may get magnetized during testing and retain residual magnetism. If it were to affect the performance of the object under service conditions, then it has to be demagnetized. Inner crack voids foreign object detection. Defects that have been sealed by welds need to be detected by radiographic and ultrasonic weld inspection. These are expensive tests. X-rays from tube or gamma rays from radioactive isotopes are directed onto the weld. A photographic film placed beneath the weld is developed after exposure to the rays through the weld. The amount of energy absorbed will depend upon the thickness and the density of the metal. The remnant energy will be absorbed by the film, and these areas will appear dark when developed. Since the parent metal also gets exposed on the same film, defects can easily be identified by comparison. This test is possible when both sides of the weld are accessible. Radiographic interpretation requires skill and experience in the field. A false interpretation can be very expensive. A radiographic test provides a permanent record of the test. It is essential that trained and qualified personnel, who understand the procedures and health and safety issues, conduct the test. In the ultrasonic test, a beam is directed towards the object through a couplant. When the beam meets a discontinuity, it is reflected back. The study of the incident and reflected beams diagnoses the size, depth, and shape of the discontinuity. Needless to say that this procedure also requires skilled personnel to handle the equipment and interpret the results. For conducting this test, accessibility to one surface is sufficient. Destructive testing. This method of testing is carried out for the certification of welders and failure analysis studies. It is also used in research and development establishments and for sampling inspection. There are various procedures adopted for conducting destructive tests. Among others, it includes micro-etching, macro-etch testing, fillet weld break test, transverse tension test, and guided bend test. Welder qualification. It is imperative to have the welders qualified and certified to undertake the work they are assigned. While a welder may be qualified from a technical institute, he has to be certified by an accredited agency for the specific type of work undertaken by him for his organization. Welders will have to be certified for steel, aluminium, and copper welding, and also for the degree of difficulty. The welders are to be monitored to ensure that they continue to possess the skill that they have been certified for. Jointing. There are different methods of jointing of current-carrying conductors in busbar systems. The most commonly used method in the order of usage is welding, bolting, and clamping. Riveting and brazing have almost become obsolete with the advancement in welding technology. In an enclosed bus system, it is suggested that wherever it is possible to make a welded joint, it should be opted for, since each bolted or clamped joint, apart from being expensive, would require access for maintenance. A busbar joint is efficient if the resistance across it is less than or equal to the resistance of an equivalent length of the busbar, without the joint. In an isolated phase bus, the most common method of jointing of the enclosure as well as the conductor is by welding. Bolting is resorted to only at the termination ends. Outdoor switchyards use tubular conductors. Welding and clamping are extensively employed. The welded area must be dressed to ensure that it does not contribute to corona discharge. Many outdoor equipment have copper terminals and may be required to form connections to an aluminium busbar. Bolting and clamping can form an effective copper to aluminium joint. Clamps are also used for holding the parallel conductors of the same phase. This is different from the clamps used for current transfer and act as current equalizers. Such clamps are necessary to limit the stresses and deflections between the conductors of the same phase during short-circuit forces. Such clamps are also used on bundled conductors in transmission lines and are referred to as spacers. Welding. Welding is the most efficient and preferred form of jointing of copper or aluminium conductors. It is permanent, does not deteriorate with time, requires no maintenance, and is extremely economical. However, welding of copper or aluminium needs expertise and specific infrastructure. Repetitive welding at works can be undertaken by robots. Welding at the site is mostly manual and requires skilled operators. Bolting. Where it is not possible to carry out welding, bolting is the next preferred method of busbar jointing. These joints have been in the industry, giving satisfactory performances, in onerous service conditions, for a sufficient length of time to give confidence to engineers. An efficient joint must have a low contact resistance, maintain its integrity during its life of the joint by containing the effects of corrosion, fretting, thermal cycling, differential expansion, vibration, and fatigue. Clamping. Clamping of conductors is extensively used in transmission lines and outdoor switchyards. In the switchyards, all the conductor joints and terminations are made with clamps and connectors. Clamps and connectors manufacturing is a very specialized and mature industry. The clamps and connectors installed in a switchyard are voltage specific, as they are tested for corona discharge. Clamping has the advantage that the ends of the bus bars do not need processing for jointing. This allows a certain amount of flexibility that is needed in switchyards where tolerances are large. When the clamp is of a different material from that of the conductor, it is susceptible to the formation of a galvanic cell. Clamping is also universally adopted in the sandwich bus and low-voltage cast resin bus, for jointing the conductors of the adjacent sections. Plating. A natural metal joint, made as per the recommended practice, is always preferable, be it between copper and copper or aluminium and aluminium. Such joints with boots and gel coats, to prevent exposure to atmosphere and ingress of moisture, have given satisfactory performance over the length of their life. International specifications permit higher temperature rise for plated, tin and silver joints, and consequently, it has become a practice to plate the conductors at the joints, thereby making the busbar system assembly more cost-effective. There are apprehensions on the life of plating and its performance under prolonged temperature cycles. A plated busbar end, tab, on which mechanical processing such as drilling and cutting have been carried out, can form several localized galvanic cells leading to corrosion. In a galvanic action, the anode gets deteriorated. However, if the surface area of anode is large compared to that of the cathode, the effect of corrosion due to galvanic cell formation is minuscule. The plating of busbar is carried out for the following reasons. It is carried out on conductors for protection against corrosion. Plating is carried out on copper and aluminium to form an efficient mating surface at bolted joints either between copper and copper or aluminium or copper and aluminium. Plating must be carried out after the busbars have been formed and worked upon. Most of the busbar joints will be installed at the site. There is a significant time interval between the dispatch from the factory and its assembly at the site before commissioning. In many sites, the bus products are stored outdoors and exposed to the elements. Hence, all plated contact surfaces of the busbars of a factory-assembled section must be thoroughly cleaned and a protective cover wrapped, to prevent surface deterioration due to oxidation and corrosion during the intervening time. A joint must not form a galvanic cell. Copper to copper and aluminium to aluminium joints have yielded satisfactory performance over the lifetime of the busbar system. Plating of the palm of the busbars for making effective joint, copper to copper, aluminium to aluminium and copper to aluminium, has been practiced to improve the joint efficiency, lower contact resistance, prevent galvanic corrosion, and enhance the stability of the joint at higher temperatures. The most common plating metals are silver, tin, nickel. Silver plating. Silver is an excellent conductor of electricity and therefore provides the least contact resistance. For the bolted joints, a thickness of 10 microns is adequate. Silver plating is expensive. The requirement of the thickness of silver plating of contact surfaces of switchgear is higher as it has to cater to impact, aberration, and arcing. Tin plating. Tin plating has been extensively used at the contact joint. There is also mounting evidence that tin plating of contacts leads to fretting, resulting in joint degradation. Further, tin forms an alloy with copper even at room temperature, rendering the joint brittle. Both these effects can result in higher contact resistance. Tin plating is inexpensive and many manufacturers carry out tinning of busbar for the entire length instead of just on mating surfaces of the tabs. Most of the sandwich bus manufacturers adopt this practice. Plating with lead tin alloy provides a shiny surface. Nickel plating. Nickel plating is cost-effective and provides a stable contact resistance. Nickel plating will make the surface hard. Its superior performance is attributed to lesser differential thermal expansion with respect to a substrate of copper and aluminium under current cycling. Painting. Painting of conductor and enclosure serves a dual purpose. It protects the surface from adverse environmental conditions. It increases the relative emissivity of the surface, thereby improving the heat-absorbing stroke dissipating capability of the coated surface. Apart from the color, the finish, glossy, semi-glossy, or matte, does matter. A matte finish increases the area for heat dissipation and consequently is reflected as an increase in the relative emissivity. The enclosures of the busbar systems that are installed outdoors may also be exposed to corrosion, erosion, and UV radiation. UV radiations will weaken the bonds and result in the fading of the original shade. Consequently, painting materials that are resistant to the detrimental effect of the service conditions must be selected. During service, the high-voltage open bus in switchyards will accumulate dust, not only on the surface but also on locations interfacing with the support arrangement. These must be blown and power washed during routine annual maintenance. Essentially, two different types of paintings are adopted in busbar systems. Liquid painting, powder painting stroke coating. Before an object is taken up for the painting, surface preparation has to be carried out. Surface preparation for the steel component comprises degreasing, pickling, phosphating, and passivation. These are carried out in a multi-tank process, in sequence with rinsing between each operation. For the aluminium component, degreasing, followed by rinsing is sufficient. Liquid painting. The liquid painting was extensively used before the advent of powder coating. After the surface preparation, moisture is completely removed before undertaking further processing. This is best achieved in an oven. A surfacer is applied for providing additional protection. A primer coat is applied with a spray gun to the surface which forms the interface between the paint and the surface. Putty is applied for covering minor adulations, deformities, dents, that may have occurred during the manufacturing process. For aluminium, etched primer is recommended. This bites into the metal and forms a good interface between the surface and the final shade of paint. Finished coat is applied by a spray gun. Enamel and epoxy are two different types of paints that are most popular in the bus industry. Paint industry is highly advanced and matured. Paints have been synthesized to meet specific requirements such as resistance to specific corrosive atmospheres, high temperature withstand capability, resistance to impact, and resistance to UV radiations. Any shade of paint with finish can be obtained from a computerized mixer. Spray painting is the most popular and economical method of painting. It provides a uniform thickness of the coat on the product. Paint that does not adhere to the surface of the object is collected from the painting booth for neutralization and safe disposal. Many specifications call for unreasonable paint thickness on the surface. There is a misconception that a thicker coating provides better protection. On the contrary, a thicker coat can lead to flaking. There is an optimum thickness that can provide the best protection. Most of the paints can be applied in glossy, semi-glossy, and matte finish. The degree of dullness is controlled by adding quartz or alumina powder of specific size to the paint. Epoxy paint can be made of a two-part system that is mixed just before the application. Though air-drying paints are available, they can never match the quality that is obtained from oven-baked. Adhesion, bonding, and cross-linking are far superior in an oven-baked surface than on an air-dried surface. Liquid paints can also be applied by brush and rollers for objects that are large and require a heavier coat, such as in the case of outdoor structure steel supports. In an extremely corrosive atmosphere, liquid paint is applied by brush over the galvanized steel structure to provide additional protection. Powder painting or coating. After surface preparation, the object is heated in an oven to attain a specific temperature. It is then transferred in the heated condition to a painting chamber. In the painting chamber, the object is earthed and the charged powder from an electrostatic gun is sprayed on the object, which attracts the paint, resulting in good adhesion. The paint powder is a single-component epoxy that bonds on elevated temperature. Powder that escapes the surface of the object gets collected and recycled. After coating, the object is transferred to a curing oven. The coating thickness of powder coating is limited. The thickness of the coat can be marginally increased by exposing the object for a larger period. It is not possible to powder coat an object that has already been painted or coated. Powder coating is done in a batch or continuous process depending upon the size and shape of the object. Large objects that cannot be accommodated in an oven or a booth need to be necessarily liquid painted, suitable for air drying. Coating. The discussion is limited to the coating of bus bars for insulation. Coating, however, additionally improves the emissivity for better heat dissipation and provides protection against the corrosive environment. Medium voltage, air-insulated, metal-enclosed bus are designed to meet the specified build requirements. Most of the designs meet the specified criteria with bare conductors mounted on insulators. Air is the only insulation between the conductors and between conductors and earth. Consequently, there is a requirement for minimum air clearance. Therefore, for a given rated voltage and bill, the enclosure size cannot be reduced beyond a certain dimension. The geometry of the conductor for a given current alters this minimum requirement. The type testing for bill withstand of non-segregated and segregated bus is carried out with a bare conductor. The coating of the conductors provides an additional factor of safety. Some of the specifications permit the conductor to be coated, insulated, and let the bus duct comply with the required bill considering the conductor insulation. The clearance between the coated, insulated conductor and between the conductor and earth can be significantly reduced and the bus duct can be made more compact. The coated conductors share the voltage stress under normal operating conditions. The ratio of the burden can be evaluated based on an equivalent circuit of two capacitances in series. In this design, the coated conductor has to undergo a routine power frequency voltage withstand test before it is assembled on the insulator inside a bus duct. The test on the conductor is carried out with the coating wrapped around by a conducting foil and a test voltage applied between the conductor and the earthed foil for a specified duration of time. It is the normal practice to apply the rated voltage, line to line, for 1 minute. Few stress the insulation to a higher value of twice the system voltage plus 1 kV. In a low voltage bus duct, the clearances will exceed the minimum requirement, with bare conductors, and therefore the coating, if carried out, need not be subjected to voltage test. The spacing between the conductors will be dictated more by the thermal consideration and short circuit withstand capabilities. The coating will only provide additional safety. The coating is carried out for flat bus bars normally used by most of the bus duct manufacturers. The conductors must have a smooth rounded edge to avoid any stress concentration. The coating material is a one-part epoxy system, which, at elevated temperature, bonds and sticks to the bus bar. Essentially, there are two methods of achieving a coat: electrostatic coat, fluidized bed coat. Electrostatic coating. This process is very similar to the powder coating. The bus bars are formed and fabricated with end preparation of the palm. The surface is subjected to buffing to remove all traces of oxide film, oil, and other contamination. The palms are masked with a heat-resistant tape. The bus bars are preheated in an oven for a specified duration and at a predetermined temperature. The duration depends upon the size of the bus bar. The preheating temperature is recommended by the coat manufacturer. The preheated bus bars are introduced into the chamber for coating. The duration, discharge, and configuration of nozzles are controlled to provide a uniform coat of specific minimum thickness. The thickness of the coat to be applied depends upon the voltage rating of the bus bar. The bars are then removed from the coating chamber and kept in a post-curing, temperature-controlled oven for a specified duration. It is preferable to cool the bars to room temperature inside the oven. Several manufacturers have a continuous process wherein the bus bars are hung on a conveyor belt monorail. However, such a system is feasible and cost-effective only when the bars are similar in shape and size. This method provides an extremely good adhesion, but it is an expensive process. Fluidized bed coating. The bus bars are fabricated, cleaned, masked, and preheated in an oven to the recommended temperature. One part epoxy powder is suspended in a custom-built, fluidized bed after ensuring that the powder is devoid of moisture. During fluidization, there will be no ingress of moisture as the temperature of the bed is significantly above that of the ambient. Preheated bus bars are supported on a spring-loaded contraption and dipped in a fluidized bed of epoxy powder. The duration of the dip is important as it provides the necessary thickness. Once a bar is taken out of the bed, a jerk ensures that all the excess epoxy on the bus bar falls back into the bed, giving the bar a uniform coat. This process requires skilled operators. The sieve of the epoxy powder is very critical and it should fall within a band, to ensure bonding. The thickness of the coating to be applied is determined by the voltage rating of the bus duct. After the bus bars are removed from the fluidized bed, they are transferred to an oven for post-curing. The temperature and duration are recommended by the epoxy powder manufacturer. It is preferable to cool the bus bars inside the oven to room temperature. This method of application is cost-effective and high on productivity. In a more advanced version of the process, electrically charged bus bars are introduced in a chamber containing a cloud of epoxy powder. This ensures better adhesion and uniformity. This process is more suitable for a continuous process with identical bars, where all the parameters of the coating system can be firmed up and automated. This is ideally suited for the bus bars of sandwich bus that are identical and require a thin uniform coat. Galvanizing. Galvanizing has been the most popular method of protection of steel against corrosion. Over a period, it has come to define the deposition of zinc over steel. The galvanizing process does not alter the mechanical properties of most of the structural steel, which is normally hot-rolled. The reduction in strength of a few parameters, even on cold-worked components, are minimal. Steel reacts with oxygen in the atmosphere to form iron oxide, rust, which is a stable compound. Steel will also corrode through galvanic cell formation, in the presence of moisture, due to non-uniformity in the surface composition. This process of corrosion continues until the entire steel is consumed. Steel is protected by the galvanizing process in many ways. It forms a protective skin around steel and prevents interaction with the atmosphere. Should there be an exposed area of steel, damage caused during transport, loading, unloading, or installation, zinc in the neighboring area will act as a sacrificial anode, protecting the steel cathode in the electrolyte. Such practices, called cathodic protection, are universally adopted in all industries to prevent corrosion. Zinc itself forms a protective envelope called platina, which prevents a further attack on the surface. Zinc, in the presence of oxygen, water, and carbon dioxide, forms a compound which bonds well and is insoluble. Any damage on the surface of the platina is self-generating. There are different galvanizing processes, and the selection depends upon the size and shape of the component, coating thickness, and service conditions. In the bus industries, galvanized sheets are used as enclosure material. Formed and rolled sections of steel are galvanized and used as support structures. Galvanizing of fixings and hardware is carried out especially when they are installed outdoors. Various methods of galvanizing are batch hot dip galvanizing, thermal spray, metallizing, continuous sheet electrogalvanizing, zinc electroplating, zinc-rich painting, sheridizing, mechanical plating, continuous sheet galvanizing, batch hot dip galvanizing. Depending upon the geometry and quantity, hot dip galvanizing can be accomplished either in the batch process or the continuous process. Hot dip galvanizing is a very popular method of providing a protective coating to the heavy, structural steel of a thickness of 6 mm, quarter inch and above. This industry has been dictated mostly by the requirements of transmission and telecommunication tower, steel bridges, lighting masts, and similar structures. In this case, most of the members are long and the bath should be capable of accommodating such long members. Consequently, the capacity of the galvanizing shop is determined by the length of the member it can galvanize in a single dip. Some industries adopt a double dip to cater to the requirements of the sections that are longer than the bath. Double dipping can also be resorted to when the width of the component is marginally less than twice the height of the bath. Surface preparation of the job, just before galvanizing, is important. Rust, grease, and other foreign objects have to be removed. Some applicators have pickling and rinsing baths. Most of the applicators resort to shot blasting, which is also the preferred mode. It is necessary to carry out the galvanizing immediately after surface preparation to prevent oxidation. The galvanizing bath is maintained at a certain controlled temperature. It is, therefore, necessary to preheat the job before galvanizing. Preheating will depend upon the profile and cross-section of the job. For some of the small members, galvanization can be carried out without preheating. Designer of the structural members must ensure that molten zinc does not get trapped in corners and there is a continuous path for the flow of zinc back to the bath. This may require additional holes for venting and draining. Fixings above a certain size can be hot dip galvanized. The thickness of the coat of zinc is determined by the shape and size of the steel component and time duration. It is a parameter that is best determined by the applicator, based on his infrastructure. The thickness of the coat is always marginally more at corners and edges, which are critical areas. Small objects can be dipped in molten zinc and spun to remove excess deposits to provide a smooth and uniform coat. It is ideally suited for galvanizing fixings, to protect the thread profile. Thermal spray, metallizing. It is the process of spraying semi-molten zinc on the surface of the fabricated item with a handgun. The two popular methods of spraying are electric arc spray process. An arc is struck between the two zinc electrodes, which are all consumables. Zinc melts due to the heat generated by the arc and is sprayed on the object by compressed air. Flame spray process. A combustible gas melts the zinc and is sprayed on the object by compressed air. A distance of 15 to 30 centimeters, 6 to 12 inches, is recommended between the tip of the gun to the object. This process is expensive and is adopted under specific circumstances. It is ideally suitable for large objects, such as masts and towers that cannot be hot-dip galvanized due to their sizes. Spraying can be undertaken on objects that would otherwise distort due to heat when hot-dip galvanized. The deposition can be much higher and can be undertaken by spraying multiple layers. A thickness of 250 micron coat is possible. The spray coating is porous with a rough surface and therefore, a final coat of paint can be given to make the surface smooth and provide additional protection. Spray coating can be undertaken at the site. Continuous sheet electrogalvanizing. Galvanized sheets up to a thickness of 3 mm, 1/8 inch, are galvanized at the mill by a process called electrowinning. As the sheets come out of the rolling mill, they are electrogalvanized. This process gives the sheet a uniform coat. While the surface offers good protection against the elements, in most of the finished products, an additional coat of paint is applied. Galvanized sheets can be folded subject to the constraint of minimum bending radius recommended by the manufacturer, without any deterioration to its properties. During the fabrication process, there are shear, punching, and other such operations that expose the cross-section of the parent material. The exposed cross-section is susceptible not only to the corrosion from the atmospheric pollutants but also to galvanic cell formation in the presence of moisture. A coat of paint not only protects the exposed section of the sheet but also provides additional protection on its non-worked surface. The indoor supporting arrangement of buzz duct is often made of formed thin sections. These are also electrogalvanized for protection. In general, the thickness of the deposit in the electrogalvanizing process is less, and therefore not recommended for outdoor use without supplementary coating. Zinc electroplating. Zinc plating is also an electrodeposition process but is carried out on small components such as fasteners, washers, etc. The components are subjected to degreasing, pickling, and rinsing before being loaded into a drum. The drum is immersed into a plating solution and rotated for uniform deposition of zinc. The plating solution was mostly cyanide, which is highly hazardous to health. It is now being gradually replaced by non-cyanide or acid chloride salt solution. The zinc electrode gets dissolved in the solution and gets deposited on the component. The thickness of the coating is low and does not increase beyond 25 microns. The surface is subsequently passivated to give extended life. Some of the components such as nuts, spring washers, and Belleville washers need heat treatment to relieve stress. Zinc-rich painting. Zinc-rich paint comprises 95% metallic zinc and is either sprayed or applied by brush on the surface of the steel to be protected. It is also referred to as cold galvanizing. Zinc-rich paint is applied when a galvanized component or structure gets damaged on the surface either during transit or during installation. It is also applied when a galvanized component or structure is subjected to mechanical operations such as shearing or drilling exposing the base strata. The exposed surfaces need to be protected. While the application does cover the exposed surface, thereby providing protection, it is more effective as a provider of cathodic protection. It is an accepted practice to apply zinc-rich primer on the steel surface that is exposed and subsequently to give an impervious overcoat of epoxy paint over it. The total thickness of the combined application of the zinc-rich primer and epoxy paint can be quite significant in the order of 150 microns. The thickness of the coat can be increased by multiple numbers of applications. Zinc-rich paint is classified based on the type of binder used during its formulation. The binder can be either organic or inorganic. Epoxy, polyester, and polyurethane resins are organic binders, while silicates are inorganic binders. Zinc-rich primers with inorganic binders are more effective in providing cathodic protection than those with organic binders. The application of zinc-rich paint on the damaged surface is only a remedial process. Improper application can lead to flaking. It is necessary to ensure that all mechanical operations, to the extent possible, are carried out before galvanizing, and handling and installation are performed without causing damage to the product. Sheridizing thermal diffusion. Sheridizing is a process wherein zinc gets diffused into the steel component at elevated temperature. Steel components along with zinc dust and inert filler are heated to about 500 degrees Celsius and placed in a rotating drum. Zinc evaporates at 300 degrees Celsius and diffuses into the steel substrate. The thickness of the deposition is uniform and depends upon the time inside the drum, and can vary from 20 microns to 120 microns. This process is ideally suited for small components such as hardware and fixings which require uniform thin coating. Unlike in the case of electroplating, this process does not result in any hydrogen embrittlement. Mechanical plating. Mechanical plating also goes by the name of peen plating or impact plating. It is an electroless process by which a ductile material is deposited over a metal substrate using mechanical energy. Copper, zinc, tin, aluminium, and tin can be plated by this process. This process is suited for plating small components such as hardware and fixings. It can provide a uniform thin coat of the metal on the substrate even when the component has an intricate profile. Unlike the process of electroplating, which also can provide a thin uniform coat on any profile of the substrate, it precludes hydrogen embrittlement. The component is descaled and cleaned. It is combined with water, medium, and surface conditioners to establish a light coat of copper. The coated piece is mixed with promoters, accelerators, and powder. The medium cold welds the metal powder to the workpiece through impact in a tumbler. The component has a dull finish which can be improved with water polish. Chromate passivation may be necessary for a thinly coated component. Continuous sheet galvanizing. Sheet galvanizing is also sometimes referred to as inline galvanizing or continuous galvanizing. This is also a process of hot dip galvanizing where steel sheets, strips, and wires are coated with zinc in a continuous manner on a coil-to-coil process. Sheets and strips of thickness varying from 0.25 mm, 1/100th inch, to 4.25 mm, 1/6th inch, thick and width of 1.8 meters, 6 feet run through a bath of molten zinc at speeds of up to 180 meters per minute. Tubes can also be galvanized by a similar process. The process comprises degreasing, brushing, rinsing, and drying to clean the external surface of the object. It then passes through an annealing furnace in a reducing atmosphere of hydrogen and nitrogen to prevent any oxidation. The steel from the furnace enters the molten bath of zinc through a vacuum chamber around a submerged roll. As the coated sheet exits from the roll in a vertical direction, an air knife removes the excess zinc and gives a very controlled uniform coat on the sheet. The thickness of the coating is significantly less than in the batch hot dip process. Thank you. Mr. Balachandran graduated with a bachelor's degree, B.Tech, in electrical engineering from the Indian Institute of Technology, Madras, India, in 1967, and obtained a master's degree, M.E., in power engineering from the Indian Institute of Science, Bangalore, India, in 1970. He is a Fellow of the Institution of Engineers, FIE-India, Fellow of Institution of Engineering Technology and Chartered Engineer, FIET-UK, and Life Senior Member of the Institution of Electrical and Electronics Engineers, IEEE-US. He was the founder-director of Power Gear Limited and Busbar Systems, India, Limited. He has worked in manufacturing industries in India and the UK and is currently an advisor. He has engineered several busbar systems that have been manufactured and installed in various countries, including isolated phase bus for the largest hydroelectric power plant, 26 by 800 megawatts, at the Three Gorges project in China. During his professional career, he has developed and tested a range of bus products and their accessories. His area of interest also includes switchgear, instrument transformers, and power system analysis. The book, An Introduction to Busbar Systems, authored by V. Balachandran, is case-bound, hardcover, size A4, 386 pages, printed on 100 GSM glossy paper. Copies of the book can be purchased with a requisition to Bala at busbarsystems.net. Black and white version of the book is for sale in India, Afghanistan, Bangladesh, Bhutan, Nepal, Pakistan, and Sri Lanka at a cost of 4,500 Indian rupees plus freight. Color version of the book is for sale in all other countries at a cost of US $126.00 plus freight.